So it's really nice to meet you in person, finally. That's really good. And welcome to our talk, Uncover More Secret, Crypto Secret with r2con2024. Before we start, just quick, I'm Sylvain. I'm an applied cryptographer at day2, so I'm mainly doing with cryptography, trying to break implementation of cryptography algorithm and protocol. I will be there today and tomorrow, but if you want to contact me, you can do it on Mastodon, and I will let Karim present himself.
So I'm Karim Sutki. I'm an IoT security expert. My main area of expertise is hardware. So in my daily job, I do hardware hacking. I mainly focus on targets. It can be a small microcontroller, but also bigger system like EV chargers and things like that. And you can find me on social media via this handle in X or Twitter. So this talk will be about how basically we use r2con for memory analysis. It has some nice features such as pattern recognition and also some nice things to recover cryptographic materials. It's also about showing you some evolution from the previous talk that Sylvain did back in 2020 about cryptography. And also it will be the occasion to show you some practical use cases that I use r2con to recover some secret in real target scenario, let's say.
So if you have used r2con, you figure out that you can search for a lot of different things, just string, X pattern. You can search for if some hash digest match in memory to some hash of some block. You can search for magic constant in the memory. But for this talk, we'll mainly concentrate for the /C, so meaning that we are searching for cryptography materials in memory or in a binary. And when you search, you have in r2con, you have a lot of configuration you can change. Basically, you can tell I want to search from this address to this address. I want to stop the search after I hit, for example, 3 result. And you can find all this configuration in the r2 book. But it really helps you to configure your search in r2con. You can do more complex stuff that when you search, you have a result, you can execute a command on a hit, that's nice. But one thing which may be problematic is when you want to have more advanced pattern, like you want to match this string and this pattern, but not this constant. And for that, you need something more, you need plugins. And as Pancake mentioned during his keynote, now, we have r2 Yara. So Yara means yet another recursive acronym, so it does not really helpful to understand what is it. I think most of you know what is Yara, but it's basically an open source tool developed by Aristotle at the beginning. So basically you write a text rule, and if this rule match into your memory dump or your binary, then it will tell you that it matched and where. So it's really useful. It's used by a lot of tools like IDS, antivirus, and even yesterday I discovered during the training of Travis Goodspeed, which was really good, that it's also used by mass_crom tools, so to create rule to search into a mass_crom. So it's really, really nice. And in r2, so you can use Yara as well with the r2 Yara plugin. So this is an example of a rule we will use during this talk. So it's really simple. You write the metadata with the author, the description, the date, and so on. Then you write your pattern, like the base point in hexadecimal. So there's a lot of way to describe your pattern. I really encourage you to have a look to the documentation. And the most important part is the condition. So basically, you define what is the logical pattern you want to match. So here we want to match the base point and one of the 2 coefficients. So it's really powerful. It will really extend your search capability in r2con. So as usual, you can install r2 Yara with the package manager from r2con with this command line. And the new thing is that now r2 Yara moved to a separate repository. It used to be an extra repository. So now if you want to have a look to the code and contribute, this is to this address you have to go. I will show a quick demo just to show you how it works. So basically, we open the binary. Then there is a preloaded rule already in when you run it. So here I'm just clearing the preloaded rule. So all the commands are YR command. Now I'm adding the rule I showed you before. I list the rules which are loaded, so you can see that there is 2 rules now. And I can just scan my binary, and I got a match. So it tells me which rule was matched in the binary and where it happened. And then it created some tags, so I can seek to those tags in memory, and it will stay during my reverse. So it's really helpful, because as soon as you, for example, here, you discover that this binary is using cryptography algorithm, because you could identify the constant. So now you can reversing from this part in the binary, because you know that it uses this algorithm. So it can be really, really powerful depending your reverse. Yeah. So of course you can you reuse some rules. I used to work with one repository called Yara rules. There is a lot of rules, not only for cryptography, but it seems that now it's a bit frozen. The last commit is 2 years old, and there's a lot of PR which are not merged. So just for waiting, I created my new repository, especially for cryptography rules, because that's the one I use most. So if you want, I will integrate your rules, and maybe the new repository will come back to life at some point. And the new one novelty, thanks to Pancake, is that now you can create your own Yara rule while you are reversing directly into r2. So the commands are yrg. So that's really helpful because you don't. I mean, if you find a pattern in a binary, you can keep it in your current rule and then reuse it while you are reversing. And it's quite easy to use. I will also show a small demo. So again, I open a binary. Then let's assume I found. I'm sorry. I found a nice string in my binary, and I say, oh, I want to keep that into my rule. So now I delete the rule again. I type yrg to see what is the current state of the rule. And now the rule is basically empty. I have only the metadata. So the rule is just, I can start working with that. So I will add the string I found at this address, which is 16 bytes. Now I will display the rule again with the same command. And now you can see that the pattern is written, and the condition is all of them because I have only one pattern, so it will match all the patterns. You can configure your rule. So here I'm just changing the name. For example, you can change a lot of things like the condition and so on. Now I will add this rule I just created to the loaded rule in radar2. I can list to check that it's already loaded. So you see that the name was updated. And I can use it as before as a standard rule. So it's quite convenient because you can just keep track of your finding during your reverse and use it in a Yara rule. Okay, now let's see what happened since last time about symmetric cryptography. So maybe you remember in 2020 I was presenting a command called /ca, which allows you to search AES key schedule in memory, because for AES, you have some relation, which will, if you have a memory dump with an AES key schedule in memory, it will allow you to find this key schedule easily, just with /ca. It turns out that we needed this feature, but for SM4. So SM4 is a Chinese standard for a block cipher. So it's the AES, but in China. So we decided to implement the same feature for SM4. So now you can just use a parameter to scan, to do the exact same thing for SM4. And we presented the result we got with this, about SM4 on some hardware attack with Baldar, another friend at Hardware.io. So if you're interested by this in particular, I really encourage you to have a look to this presentation. But for R2 user, maybe one thing to mention is that For SM4, there was one thing a bit different. Like for AES, the secret key is directly into the key schedule. For SM4, it's not the case. You first XOR your secret key with some constant, then you do one round of encryption, then you discard, you get the first round key and you discard the first secret key. So it means that you will find the key schedule, but the key is not present in memory. But you can forget about this scheme because we just added in r2 a small message which will reverse this round and display the correct key value for you, so you can reuse it without bothering like what is the key value at the end. But still in memory, you can see that the first round key does not match the secret key. So that, I think it can be also helpful for you. Also, while we were working with Karim, we use a lot the WOD and WOE command, which will take a block and write over this block its decryption or its encryption with an algorithm. But we figure out that sometimes we don't need to directly write into the binary, but just check what is the decryption of this block or the encryption. So we added two simple commands, POE and POD, and you can just use them to print the decryption or encryption of the current block of your binary. And here is the current list of the supported algorithm. You can just print them in and see what's supported. And so that was the theory, and now I will let Karim explain how he used it for real project and how it can be useful for practical application.
Yes, so once I came to work and basically customer gave us a device that I need to have a look on, and this device turned out to be a standard PC, let's say a big PC with FPGA connected and other things. It turns out that this PC was using a Linux operating system, nothing fancy about that, but it had a lot of features enabled, such as secure boot and full disk encryption. The nice thing about full disk encryption is that they were using this trusted platform module. If you are familiar with it, it's fine. If not, it's just a hardware component where you can send cryptographic materials and it would be stored in a secure fashion, so you cannot retrieve it without having the correct conditions. And the goal was obviously to first decrypt the disk and start to have a look on what's inside the system. So just to understand a bit how it works, so basically if you want to encrypt a disk, you will seal a key or a passphrase, which is not the master key to decrypt the volume, in the TPM. And during boot, what you will do is the system will measure each component that will be run on the system, and it will compute a hash that will be stored in a register, which are called platform configuration register. There are up to 23 of them, 24 actually, but some of them are used for user usage and others are for the system. So, for instance, PCR0 is used to measure components such as the BIOS and other firmware components. So you will have the hash and it will be extended with all the components. And for instance, PCR1 is used for the configuration of the BIOS. So whatever configuration that you had in the BIOS will be hashed and stored in this value. And it turns out that the key is released only if the PCR matches. So the condition for this specific use case is that you provision the key when you boot the system and you know it's trusted, in a trusted state. And then you will ask the key whenever the system was booted without tampering. So it means that if you change the command line or you add some things or you try to tamper with the device, it will not work. So disk won't be encrypted and you will be having a nice message on the screen. So on a practical perspective, it's fairly easy to do. There have been a lot of noise around it. It's a simple and low-cost attack. Basically, you can either do it very cheaply by soldering wires on the pins, because since it's a component that sits outside on the motherboard, you can do it. Some guys did tools. So here you have a tools from Stack Machine that fits very good to this connector on this laptop. And what happens is that once you are set up, you will just monitor the signals with the logic analyzer, wait for a specific command, it's the unseal command, and then you get the key. So on the right side, you can see that there is a Pico TPM sniffer, it's the tool above, and you can see that the guy recovered the BitLocker key in a few seconds. It took him, with the tearing down of the laptop, 43 seconds to get the key. Of course, then you need to do some things on the disk, but it shows you how easy it is. However, on my setup, the TPM is quite different. So TPM is not sitting just like this, which is called discrete TPM, but in fact, it's incorporated inside the CPU. So on Intel, it will be platform trusted technology, sorry, and on AMD, it's called FTPM. So at this point, I was quite fed up. So where I can put my probe, what I will do, because I cannot recover the signal easily. And at that point, I said, oh, smart move from the customer. So then I started to wonder, is it really a smart move? Can I do still something? Because maybe there's other ways to get inside and recover the key. So luckily, the BIOS password was not set. Don't ask me why. And as I explained before, the BIOS settings were not measured as part of the boot process, which means that you can modify these settings. So then you ask the question, what shall you modify? And can I modify, for instance, secure boot? Unfortunately not, because if you modify something in the BIOS or reset the BIOS, you will erase the key and it won't work. Then you say, oh, there is nice features such as Intel VTD. VTD is for virtualization technology. You use it when you need to run an hypervisor, for instance. And what happens is that when you enable this feature, it will enable the IOMMU, which allows you to separate the memory and isolate each memory region for the others. So this means that you can do DMA attack. What is fun in this specific use case is that the Linux operating system was installed using UKI, which means a unified kernel image, and therefore you cannot change the kernel parameter because it's encompassed inside the image. So in this case, they didn't have Intel IOMMU on, so it's even easier. You don't need to disable Intel VTD. It will not be taken into account. So to do direct memory access attack, you just use some tools. There is one that works pretty well. It's PCI Leech. So you plug it inside the PCI slot, you boot the system, and you connect your laptop with this device using USB-C. You'll launch some commands. The FPGA will do the thing and dump the entire memory for you. And then you use your favorite commands in r2con2024 to find a key expansion in memory and decrypt the disk. So here I prepared some small demos. However, it's anonymized, of course, and I did it on a VM, but it works in practical the exact same way. Bear with me. So here, for this demo, I just narrowed the search because I know there is only 2 hits that I need because my system was using XTS 512, so this means that you have 2 different keys that are being used with 256-bit encryption keys. And once you recover them with a r2con2024, you can just reorder them and decrypt the disk. One other nice trick is that for crypt setup or those setups on Linux, usually when you have an offset of 0x1f0, this means that you have the 2 key expansion for the disk encryption, if it's using this thing. This can be also seen if you dump the LUX header. Once you get access to the system, you can see that the bytes match. So you will have first key and second key on the second row, and then you can access the disk. If you turn out to access a Chinese system, this will work the same way as Sylvain mentioned previously. In this case, it's also the same story. You use 2 keys for the encryption. I don't know if there is any pattern for this one, but you can see that we recover the key. And if you look closely to the bytes, you can see that the LUX header match as well. So this means that you will decrypt the disk and get access to its content. Then you can perform usual stuff, like reverse engineering the binaries that lies on the top of the file system, the application of the customer. And of course, this led to some discovery. So there were multiple RCE as root on the system because it was badly coded. So just to see the impact that it can have. So now we'll switch from symmetric crypto to asymmetric crypto. There are a few things that you can do as well with r2con2024. You can search for certificate. You can search for private keys as well, or other keys and signature for GPG or PGP. It's quite convenient. You can also, when you have a hit, you can use the PF whatever commands that will display you the decoded version of this. So you will see it in a human fashion, in an understandable fashion. And it's quite convenient. So for this target, so this particular use case, I had a device. It's a standard IoT sheet where you have an ARM microcontroller. And it turns out that those guys let r2con serial console, open, no password, nothing. And there was a shell, custom shell inside, where you could run some commands. So you could read from an arbitrary location and write to an arbitrary location. So I used it to dump the microcontroller firmware and then to dump the external memory as well, because it was free, so I used it. On the external memory, on such devices, you often see that people will store specific assets, such as certificates, settings, whatever. In that case, the device is connected to the cloud directly via Wi-Fi, so without any application, because usually you will have your app that will do a proxy, get the data out of the device and send it to the cloud. Here it's direct connection. So often what I do is just, I fire r2 and I just hunt for certificates. So this is what happens when I do it on my memory. So I just load my memory dump. I switch the block to a bit larger than usual, by the default one. Why? Because it will be used further on for the print commands. If you don't do it, you will have a nice error message. So I just increase the block a bit. I can range it even more if needed. And when I do /cr, so it's to find the private key. I find 2 hits. So at this point, I'm like excited. However, if you use the command to print what's really inside, you can see here it's actually a template. So it's a certificate request, and it's a certificate request, this one, and the next one would be a template for a certificate. So it's not useful. You cannot do anything with it. So then I fire /cd to search for a certificate. I have a hit, and then I will use again the command to print the thing. So on the screen, you can see that the command name actually is a MAC address. Here it's anonymized, of course. We can see the validity of the certificate, and we can see there are several fields. Here there is a public key, so we can confirm it by just running the pfx command on the same offset, and you will see that it's using also a curve, ED25519, and I was not quite I didn't have any knowledge on this, so I found this public key and I was like, okay, that's fine. And before going forward, I think it's up to, so so I found this public key, but I didn't find the private key as we saw before. So /cr didn't find any private key. What you can do is when you have a memory dump, to give you an indication if it's encrypted or not, you compute the entropy of the binary. And then you can see on the right side that the blocks, the entropy is not that high. I mean, if it's encrypted, you will see it's super high all along the binary. Here it's like just a few of them, and maybe it's even not encrypted or not, just compressed some part. So, okay, then I went back to my firmware. I started to reverse engineer my firmware. I saw some pointer to the external memory, but still, I was wondering why I could not find the private key with /cr. So I turned around to my friend Sylvain, And I asked him, yeah, how can I find the private key easily?
So first, maybe the ED25519 algorithm, maybe it's not well known, but it's quite used a lot in embedded device world because it's basically like ECDSA, but you don't rely on the random number generator. So basically, you won't have all the vulnerability like the PlayStation 3 epic fail. It's quite small. The code is quite small as well. The key generation is fast. And also you have small keys and small signatures. So it's more and more used in the embedded world. So maybe you will see it during your project. And we were discussing with Karim because he told me, okay, I have the public key. I'm almost sure the private key is in my binary. So what can I do without reversing everything because it's a lot of work? And we were thinking, okay, you have the public key, and you know that the public key is the private key times G, and G is just a base point. It's defined in the EDDSA standard, so it's known. So a stupid idea, but you can just take your memory. You assume that the first byte up to the 32 first bytes would be the secret key. You multiply by G, and if it matches the public key, it means you found the private key. And if not, you just continue as a sliding window until this relation is matched. And if it's matched at some point, it means that this is the private key. So I told Karim, that's the idea, go, implement it.
Yeah, just do a multiplication. However, for me, it sucks big time. Like, what the fuck those cryptographers are doing? How can I can sort myself out? And then I decided just to go for this Python script. I don't give a shit. So I basically loaded the public key. Then I used the sliding window mechanism, just taking 32 bytes at a time, consider it as a private key, compute the public key, and compare the results. And whenever you have a match, boom, you can see it was found at this offset, which is just located before the public key that I found. Then I was starting to wondering, because usually my best teammate here loves r2, so I said, oh, maybe this feature can be useful to others. And then I asked for a feature request to the crypto team, meaning him. And yeah, and then he says, oh yeah, let's add another command to r2. There is not enough. So he just generated a PR and done.
So ta-da, there's a new command, /cp. So basically it will just allow you to search, if you have the public key, it will allow you to search the private key in your binary, just tapping /cp, the algorithm parameter and the public key. So far there is just ED25519 supported. As always, PR are welcome. Maybe in the midterm, the goal would be to support SSL algorithm so that you will have all the signature from OpenSSL. As usual, if you're not happy with this feature, we will refund your premium license to all of you, no problem. And also during this project, we also figure out that it's sometimes nice to be able to print the signature of a block. So we also created a POS, so it will print the signature of the current block with the algorithm and the private key for this time. So yeah, it's something you can already use now in r2. And yeah, I will let Karim show how it worked on his project.
So basically, I took the same example as before. I just put the max hit because we know that there is one single private key, and if not, it will run forever. So again, we just do /cd, we get the hit, we print some, we print this, and then we'll seek to a specific offset. I will explain a bit what's going on here. So here we go to the offset of the public key, which is 0x81. Then you have the header of the ASN1 structure that you need to skip. And then because it's a bit string, there is an additional 1 byte that will be added for sign of the value. So I need also to skip that because the value that I want is actually starting with F0 whatever and 32 bytes. Oh, sorry. I mixed up the commands. And then, so I will just stick to that offset and use the 32 bytes that are at this offset to search for the private key. And as you can see, you can find the exact same private key that I showed before using r2con2024.
Applause.
So this allows me to recover the public and private certificate. This device, I could impersonate it against the cloud, which was quite useful because firmware updates, for instance, were protected, so you couldn't access it publicly. So it was nice. I could also fake telemetry, and I can do further attack at scale because now I have access to the cloud, so it's quite convenient. So we hope you enjoyed the talk. We wanted to show you that r2con can be used in many situations, not only binary analysis. We hope that you had a good grasp on the evolution of the cryptography related commands and that you will use it in your upcoming projects. We would like to thank you for the attention, also Pancake for the venue, and if you have any questions, just if we have time, we can answer that right now or later on during the conference. Thank you.